The next chapter is discriminant analysis. Discriminant analysis is perhaps the oldest methodology for classification of nominal targets. It's been around for a long time. And the basic so it's been used as a classical statistical technique as well as data mining technique, and it can also be used for classifying observations into groups, or what is called profiling. So you have clusters of observations having similar characteristics. So let's take a small example to illustrate the concepts. So we go back to the riding mowers example, where we have two predictors, lot size and income, and the outcome is whether the householder is an owner or non-owner of riding mowers. Okay. So we create a scatter plot, income on the x-axis and lot size on the y-axis. And let's suppose we draw manually a line that separates the observations. So if we use this straight line as our classifier, so anything underneath is classified as non-owner, anything above the line is classified as owner. Then this line will misclassify four observations. So this one and this one, these two are owners, but will get classified as non-owners, and these two are non-owners will get classified as owners. So number of misclassifications for this line, okay, this line discriminating owners and non-owners, is 4. So discriminant analysis works like this. It comes up with a function called discriminant function that calculates a score, and based on a score you then classify as owner or non-owner. Okay. We're going to use an example of our universal bank, whether a customer will accept a personal loan offer. Okay. And let's look at just two predictors. The data file itself has lots of predictors, but we want to use only two: annual income and average monthly credit card spending, CCAVG. Okay. Now if you plot the two predictors, annual income and monthly credit card spending, for only sample of 200 customers, then you see that you get a plot like this, and a discriminant analysis going this way or this way is going to have lots of misclassification. So especially around here, there are a lot of events and non-events clustered together. Now here is all the 5,000 customers in the data set. Again, a scatter plot between annual income and monthly credit card average spending. Okay, now let's look at the algorithm for the discriminant analysis. So the idea is to classify a new record, okay, measure its distance from the center of each class. So you have class of owners and class of non-owners in the case of riding mower. But in the case of universal bank, you have a class of those who accept the loan offer and those who do not accept the loan offer. Okay, so find the center point of these two classes. Okay, all the records which are accept loan offer, all the records that do not accept loan offer, and you find the midpoint of all the predictors, and then find the distance for the new record to each of these two groups and classify the record to the closest group. Okay. Now, so if that's the methodology we're going to use, so we have to now figure out how do you determine the center of the group. Okay, group class equal to 1 and group class equal to 0. So, and this center is called centroid, and that is a vector because you'll have bunch of X predictors, right? So you find the average of each predictor. So this vector is a vector of all the averages. So let's apply this to a very simple case of just one predictor. So now you separate the observations between two classes, right? So here is the riding mower example. So you have all the owners, the income of all the owners, and income of all the non-owners. So you find the average income for the owners, find the average income of the non-owners, and when new records come in, so for example, a new record comes in, the income is 50. So the distance between 50 and 79.48, and the distance between 50 and 57.4 gives you these values. And see, now this income is closer to the average income of non-owners, so you classify as non-owner. 60, the distances are these two, and again this is much closer to non-owner, so classify as non-owner. For 70, it's closer to owner, so classify as owner. And 80, the same thing. Now if you have more than one, then again, so suppose for example you have income and credit card spending. So you'll have an average income, an average credit card spending for owners, an average income and average credit card spending for non-owners. So you'll have two values for each, and a new case will have an income and credit card spending, and then you can find the distance using the distance measure, like the X value of income minus the average income, square that, X value of credit card minus credit card average, square that, and add the two and take a square root of the sum of the square. So that will give you the distance, okay, to the owner group, and do the same for the non-owner group, and whichever is closer you assign. So when you have two predictors, you need to compute the average of the two predictors for each group of the target. So you have income, which we already did. So now you have lot size, again broken down between owners and non-owners, and you have the average lot size for owners and average lot size for non-owners. Then when new observations come in, so here are the vectors of means. So we have for owners one vector of average income, average lot size. Then for non-owners you have average income, average lot size. So when a new observation comes in, so okay, you have X sub 50 income, X sub 2 is 15 lot size. So you find the distance, so 50 minus 79.475, so that's the difference between these two, square that, and then the lot size, again subtract the average, square that, then add the two squares and take a square root, and you get the distance. And this is, since we use the means of owners, that's the distance to the centroid of the owner group. And you do the same thing with the means vector of non-owners. So 50 minus that squared, then 15 minus that squared, and then square root of the sum of the two, and then you get the distance. So here the new observation is closer in distance to non-owners, so you classify as non-owners. You repeat this computation for each of the new cases and compare the distance, and based on the distance then you classify them as owner or non-owner. And when you extend this to any number of predictors, so we looked at one predictor and two predictors, so now when you have multiple predictors, then your vector here is going to be much larger than just two. So you'll have one for income, one for lot size, one for the next one, another one, and another one, another one. So you'll have a bunch of means, and you will find the difference between the actual X values and the mean value, square them and sum them like what we did here, and take a square root, and that's your distance. Now, when we do that, so in case of many predictors, right? So you use the Euclidean distance. This is called the Euclidean distance. So if you have only two predictors, then you'll have that and another one for x sub 1 bar and x sub 2 bar. So if you have lots of predictors, then you do the difference for all of them, square them, add them all, and then take a square root, and that is called the Euclidean distance. And of course, for the Euclidean distance not to be overwhelmed by predictors with really, really large values, you must normalize them. So since the distance measure is sensitive to scale, and you don't want any particular predictor to overwhelm the value of the Euclidean distance, so you do normalize. And again, unequal variance also is a problem, and we'll talk more about that. And for but this measure of distance ignores any correlations that may exist between the predictor variables, and that is handled by what is called Mahalanobis distance.